we'll get started. So this is where I finished last Friday. What I'm trying to do this morning is record this on Zoom rather than Echo, because Echo live transcript didn't work for you last week. You could see it, I hope, afterwards, but you couldn't see it during the lecture. So this morning I'm trying Zoom, and hopefully there are people live on Zoom at the moment, so hopefully they can see and hear, and yeah, that's better. So, as I say, this is where we got to last week. We were talking about T-sizing, which is transistor sizing, and looking at the problems you get if you don't T-size consistently. So the point of T-sizing is that you can match your thresholds, and it also is important from a timing point of view. And that's what we're going to look at next. So if you look here, we've got, if you remember, if you vary the ratio of the width of the PMOS to the width of the NMOS, so that's this WP and WN. So I'm trying to. So here we've got three different ratios of beta N and beta P. So what's happening is you've got a single rising input, this is Vn in red, and this signal is going to three different inverters, and each of those inverters has a different ratio of the widths, and therefore has a different ratio of the gains. So you can see beta N over beta P greater than 1 for the top one, that's one ratio. The gains are matched here, and here the gain for the N type is actually smaller. So you look at those three gains, and what happens? Well, essentially, the timing is different for each one of them. So as the rising input reaches each of those three inverters, remember that the inverter starts to change when the input signal goes up beyond the threshold for that particular inverter. So this is the threshold in the center here for the middle blue line. That's the one where the gains are matched. But if the ratio of the widths are different, then they'll either react earlier or to react later. So what you can see that there's different delays for different width ratios. And that's for a rising input, falling output. If you switch that round and had a falling input and a rising output, then the same thing happens, but it's the other way around. So the times are ordered in the opposite direction. And this can be a problem, because obviously if you've got a large circuit with lots of different logic gates in it, and they are all moving at different times, it makes for problems. And in fact, there's no point in having a circuit, or there's no point in having one particular path being very fast if other paths are slow, because you always have to wait for the slowest path. So it's better to have everything as close as you can to being synchronized. Of course, it'll never be perfectly synchronized, but the aim is to have them matched as well as we can. So yeah, for large circuit, matching is important. Okay, so I want to move away from that area and think about something else, which is called fan out. Now, fan out is essentially, we're looking at, you've got one, we're talking about inverters, but it will apply to other gates. One gate, how many other gates does it drive? How many other gates can it drive? So it's a measure of the load at the output of a gate. So if you've got one gate driving one gate up here, then the fan out is one. So you've got one inverter driving another inverter. We define that as a fan out of one. If it's driving two inverters, then it's a fan out of two. If it's driving the four inverters, it's a fan out of four. And so in this simple case, it's just a matter of counting the gates. So it's easy with identical inverters, but of course, when you're building a circuit, your circuit isn't going to be just made of identical inverters. So we need to think a bit more generally about how that works. The reason it's important is that if you increase the fan out, you increase the load capacitance. And so a big fan out will actually reduce the rate of change of voltage with time, so it makes things slower. You get bigger delays, and eventually, if the fan out is too big, then you can compromise your noise margins, and so actually you don't get a proper switching event at all. One of the nice things about fan out is that you can use it to fairly simply predict propagation delays. Of course, as I said before, there are different ways you can predict how a circuit's going to work. You can do a model in the computer, and that's going to give you a nice, accurate answer if your model is good. But the problem with a computer model is that it doesn't really give you an intuitive understanding. So that means that every time you design something new, you've got to go to your model and say what's going to happen. Whereas if you can have some, even if it's fairly simple, intuitive understanding of what's happening on the circuit, then it really helps the design process. You will eventually need to check with your model that your intuition is correct, but understanding how these things interact with the load, you would basically half the dVdt and you'll double the delay time. So that little plot shows you the delay time pictorially decreasing with fan out. So for some chips, if you're designing things with, to actually build a circuit out of discrete components, you can just count the chips. In VLSI, we can actually control the fan out with T-sizing. Now, we know that a large gain comes from having a large device. So the gain, beta, is given by this equation here, and it's got W divided by L. So if you increase the width, you would increase the gain, makes a bigger device. So a big device can source or sink more quickly. So that means, for instance, if you've got a wider transistor followed by a narrow one, that would be fast, and vice versa, narrow one followed by a wider one would be slow. Of course, what you really want to do is have all your gates working roughly the same speed, and so we need to match the gains. So, okay, here's some notation I'm going to go through. If you look at the gain, beta, it's got a part circled in blue, which is essentially material constants. It's mobility, the oxide thickness, epsilon. These are all fixed constants. Then you've got the geometrical side of it, W over L. And so when you're looking at your inverter, the thing you can actually change is the width divided by L. But of course, we tend to keep L constant throughout our circuit, which means actually the thing we're looking at is simply the difference between the widths. And so what we're going to do is define a unit inverter. And the unit inverter has a width Wn for the NMOS, which is Wi. That's my unit inverter width. And WPI is the unit inverter width for the PMOS. And we use this as a benchmark for our calculations. And then we say that, well, actually, WPI is a known ratio of WNI. So that ratio RI, we've discussed that last week. It's typically round about 1.5 or 2. 2.7 would match the gains exactly, but you tend to go slightly smaller, so you have a compromise between the size of the circuit and the perfect matching. So let's assume RI is 2 in that situation, but we'll keep it as another parameter. So the gate capacitance is a bit like a parallel plate capacitor. So at this point, we're going to only think about the capacitance of the transistors in the gates. We're not going to concern ourselves with the capacitance of the interconnects. Now, later on in the course, we will think about interconnects and the fact that there are capacitances associated with those as well. But to begin with, we're just going to think about the capacitances of the gates. So for a single unit inverter, the input capacitance is given by this standard equation here. And if we say that Ri is our ratio, then we can simply simplify this. We can get rid of the WPI and just express it all in terms of WNI. And then we can lump a lot of all this together as our capacitance Cn for the NMOS. So yeah, that's the basic equation there. So this is saying that the capacitance of the unit inverter is just 1 plus some ratio times the capacitance of the NMOS. Okay, so it's fairly straightforward at that point. Now what we're going to do is we're going to consider the load transistor, or load gate, I should say, sorry. So highlighted it in red here. So for a single gate, the input capacitance is again this equation here. And what I've introduced here is a scale factor F. Okay, so Fj. The reason you've got a J there is we're counting, and we can have many different loads, or we have many different gates on the load if you've got a large fan out. So each one has got its own scale. So the scale is simply the ratio between that particular gate, the widths on that gate, and the widths on the unit inverter. So if it was another unit inverter, the scale would be 1. If it was wider, the scale would be greater than 1. So that basically, if you just plug it into the equations, just simply says that the capacitance is just simply Fj, it's our ratio, times the capacitance from the unit inverter. Then, of course, if you've got a fan out with multiple gates, what we're going to do then is we're just going to sum them up. So here we've got n different gates. We've all got different ratios, F, J, I've got different numbers here, but of course you can have any set of numbers you wanted. Just add them up together. And of course, what's the total? I've just said FL, so for the load. So the scale factor for the load, FL, is just the sum. Now we're going to consider the driving transistor, and we want to start looking at the propagation delay. Now, remember the propagation delay, TPD, is given by this equation here, which is some constant K times the capacitance divided by 2 beta and the voltage VDD. We know what the gain beta is, and we know that we've got some scale factor FD for the load. So we can put all that together. So we're going to scale the output gate by the factor FD for the drive. And this gives the gain for the NMOS, beta N. And here we have the gain for the PMOS. We're considering them separately just for the moment. But simply the gain is simply the gain you'd get in the unit inverter multiplied by the factor F. Then we have two propagation delays. So the reason I've split it is because you've got this propagation delay up down and the propagation delay down up. Okay, so remember that when you are putting the signal down, it's the NMOS that does that, and when you pull up, it's the PMOS that does that. So we're just splitting the two out because they could be different. So this is the output falling high to low, and the other one's low to high. But the only difference is the gains for the two different transistors. There are quite a few terms in that. So what we can do just to make life easy for ourselves is to lump a whole series of the fixed terms together in a single term, which is an impedance M. So I've got this impedance M here, which is our constant K, VDD, it's got the oxide thickness and so on. So all these fixed terms, including what is now fixed also, the width of our unit inverter. So if you look at that, it'll have a resistance of ohms, and that just makes the equations look a lot easier, because then you've got the propagation delay up down to be that impedance M multiplied by the capacitance divided by F. So that then is relatively simple to understand. If you increase the load capacitance, the time increases, which is what you'd expect. If you increase the width of the drive transistor, it goes down. Again, that's what you'd expect. And it's just that ratio multiplied by our impedance. And the difference between T up, down for the P and the N is fairly straightforward. It just depends on this M, the impedance, and that varies between the two. So what we have is that if you increase FD, you get bigger transistor, you get a lower output impedance, greater drive strength, and better pull down. But of course, you have the penalty of a bigger transistor. So now the propagation delay is given by this equation here. We've got the capacitance of the load. Of course, the capacitance of the load also is simply the scale factor F for the load multiplied by the capacitance of the unit inverter. Okay. So if we put that into the equation, we then see that the thing that's really important is this ratio F load divided by F drive. So it's a ratio, it's not an absolute number, and it lets us define a relative fan out, which is just that ratio FL divided by FD. And that gives us the propagation delay is simply going to be that relative fan out multiplied by the impedance multiplied by the capacitance. So the whole thing becomes relatively straightforward at this point. You've got a drive scaling factor of 1, load scaling factor of 1, then your propagation delay is just simply M times C. I'm using the numbers here for the unit inverter. Of course, if you've got a bigger load, then the time for the propagation delay goes up by that ratio, so it goes up by a factor of 4 here. And then you have more complicated situations where you have a wider drive and a load made up of various different components. All you need to do is add up the scale factor for the load, divide it by the scale factor for the drive, and that gives you your propagation delay. Okay, so if we think through what we've done this lecture, and of course, at the moment, my lectures are sort of stretching between 2 lectures. I'm going to cover eventually, I think, 6 lectures and 7 periods. That's just the way it's going. So the circuit properties are essentially determined by the physical parameters, and the silicon properties are outside the designer's control. But what we can control is the gate width. And so T sizing or transistor sizing is essentially varying that gate width appropriately to set consistent thresholds, noise margins, and speed. The fan out is an important parameter. It's a relative number that helps us to understand how timing works. Pull up and pull down are different. They can be kept fairly similar, but in general, they are slightly different. And the propagation delay can be different across different gates. And so it's important to try and minimize those differences. Right, I'm going to close this one down and start the next one. Okay, I've just gone through that, so I'm not going through it again. You've been reminded the same thing twice in 2 minutes. What we're going to now look at is some more gates. So the only logic gate we've looked at so far is the inverter. And of course, if you're designing the VLSI, you need a much bigger range of gates than simply an inverter. So we're now going to look at a whole series of other logic gates. So The first one I'm going to look at is a NAND gate. So you should all be familiar with NAND gates. It's fairly straightforward. There's the truth table, there's circuit symbol. It's essentially AND gate followed by an inverter. You can think of it as two switches in series, if you like. And the circuit diagram standardly used for this is relatively straightforward. It simply consists of four CMOS, so four transistors, two PMOS, two NMOS, shown here. But I haven't shown, let me switch this pointer on. What I haven't shown is that this is the VDD power in, and this is ground that is shown. Wiring looks a bit messy there, so what we generally do is we draw it like this. So we've got A and B inputs coming twice. Of course, they're just joined together with a piece of wire. And so how does that work? If you just look at that, if you want to pull the output down, both A and B have to be on. So if you give A and B a high signal, then both those transistors are on, Z is pulled down to 0, and that then satisfies this line here. Need to check for a crowbar current, but of course, if both those are on, that means that both those are off, so we're fine there. And then if either A or B is on, and the other one's off, so one on, one off, then this becomes short circuit. So one of these switches off. So this becomes an open circuit. One of these will switch on and Z will be pulled up. And of course, if you've got 0, 0, it's also pulled up and you get the right functionality. So the other thing you can see from here is that when we were talking about fan out, you can see immediately that if you had an inverter, for instance, driving a NAND gate, then you got a fan out situation because you got 4 transistors as your load here, whereas in an inverter, you had 2 transistors as your load. So different logic gates have different numbers of transistors to make them work. So what about other functions? That was NAND. I sort of pulled it out of a hat, like a rabbit out of a hat. How do we actually design different functions? There are some basic rules which let us put together arbitrary Boolean expressions. So it's relatively straightforward. So any Boolean expression we can very quickly turn into a circuit. And the basic rules for CMOS design are quite straightforward. You split it into N blocks and P blocks. And we saw that for NAND, and you saw that for the inverter as well. You've got a group of N transistors, you've got a group of PMOS transistors, you've got your output in the middle, always works like that. And essentially what we need is that every series N block, so here's a series N block, has a complementary parallel P block. So that's in series, this is in parallel. And likewise, if you had a parallel N block, you would have a series complementary P block. We don't have that in this situation. So that's the basic rule. So that gives you a NAND gate. So if you did put your parallel circuit in the NMOS side, you then end up with another gate because you've got parallel on the N side, and therefore you need series on the P side. And if you do that, well, how does this work? You can go through the circuit bit by bit. And if we did that, we'll find it was a NOR gate. Okay. So for instance, with a NOR gate, you would say it's OR followed by an inverter, of course. And if both A and B were low, then both those transistors would be active, and you would pull this high, which is correct. But if either A or B is high, then one of those will switch off. So this becomes an open circuit effectively, whereas one of those will switch on, or both of them will switch on, and it's pulled down. So if either A or B is high, it'll pull down, and that's the correct outcome for a NOR gate. So you can see that does work for a NOR gate. And of course, this is the simple one we had right at the beginning, which again follows the CMOS rule, and that's the inverter. So the simplest combinations are all negative. And in fact, basically with the CMOS rule, you always get this negative output. So if you wanted to make an AND gate, you would need to make a NAND gate and follow it with an inverter. Okay, you can't, using this technique, directly produce an AND gate. So that's summarized in this table here. So if you want AND, it's NAND then NOT. If you want OR, it's NOR then NOT. The next three are basically the ones we've seen, so that's fine. And then the final one is exclusive OR, and that's a bit messy. If you want to get an exclusive OR, you can write it like that. And so you can imagine there's a lot of transistors involved in putting that together. And there are other ways to put together an exclusive OR gate, but I don't want to focus on that just now. But we can do more complex functions than that. So what we want to do is look at this situation here, and essentially we're going to follow the CMOS rule, which remember is that you've got a series N block, you've got a parallel P block, and every parallel N block has a complementary series P block. So let's look at this logic function here, which is A, B, C all ORed together, and then the output of that ANDed with D and then inverted. Okay, so that's a relatively complicated logical function. So what we do is we do the green bit and then we do the blue bit. So the green bit, we've said, well, okay, that's 3 transistors in parallel on the N side. And that's generally what you can see. If you've got N MOS transistors in parallel, then if any one of them turns on, then that whole block conducts and pulls the output down. So that gives you OR functionality. You need to have series in the N side to give you AND functionality. So we've got the green one giving us the OR. We've now got the blue one giving us the AND. And so we had these in parallel here. So of course you've got them in series on the P side. Now, when you then add the other transistor, so we're wanting to have the NAND or AND functionality with D, we need to put it in series on the N side and parallel on the P side. And what you do is you essentially treat your previous 3 transistors as a single unit. Okay, so you treat those as a single unit, and D becomes in series with that unit. And again, up here, you treat those three transistors as a single unit, and D becomes in parallel with that single unit. And that's how it all fits together. And you can build that up into more complicated circuits. So what you can see, though, is that you always end up with an inverted output. So essentially, what you can do is you can have something of this form here, where you've got a whole series of inputs which are ANDed together, ORed together, and so on. But the whole block is eventually inverted. So every AND means you have NMOS in series, PMOS in parallel. Every OR is the other way around. And if you do that, you can nest it, and you can have as much complexity as you want, because remember, once you've got one block working, you can just put the next block in parallel or series with it. What you find is that you have some standard types of gates which are defined, and you have two families of them. You have the AOI, and or invert, and you also have the OAI, or and invert. Okay, so just looking at the AOI here, what it basically means is you've got a series of AND gates, one between A and B, one between C and D. They're ANDed together, and then they're ORed with, well, the output of A and B, C and D goes into the OR. And then you have other inputs into the OR, so just E and F, which weren't ANDed with anything. And that's called AOI 2211. So you can see why it's called 2211, because you've got two in this AND, two in this AND. This is like an AND with just one input. This is like another AND with just one input. So it's 2211. So that's a nice, easy naming convention, and it helps to put designs together. And of course, yeah, we always need the inverter at the end. So here's another example. So that's A plus A or B, ANDed with C or D, ANDed with E. So that one now is OR and invert, as I mentioned earlier. And that's 221 in that situation. So it's a relatively straightforward way of putting things together. What we want to start thinking about is T-sizing for these gates. And before we jump into T-sizing, we want to start thinking about stack depth. So if you've got a series of transistors in series, as I've shown here, so this is one of the circuits we saw earlier, that inhibits current flow. So if you've got two transistors in series, you've got twice the impedance, essentially. So what we can do is we can define a stack depth for a complex gate. And the stack depth is relatively straightforward. You just add the number of transistors which the current path passes through. So here, the stack depth is 2. So between Z and ground, you go through 2 transistors. Whereas that has a P stack depth of 1 there, whereas on the other side, the stack depth is 3. Okay, so we're just counting transistors. How many transistors would a path go through to get from the power rail to the output? So if you look at a NAND gate, NAND 2, that's 2 inputs, you end up with P stack depth is 1, and the N stack depth is 2. You can see that fairly easily from here. So if you kept all your widths now to be the same as the unit inverter, what happens? Well, the pull-up will be just as good. Now, pull-up, I'll come back to that in a second, sorry. And pull-down is going to be half as good because it goes through 2 transistors. What I was going to say, it depends a little bit on which inputs change at the same time. Of course, you could say if A and B changed simultaneously, then it's different to A being first or B being first, but we'll not go into that at this point. We will look a bit at that later. But essentially, the important thing here to note is that pull down is worse because you're always having to pass through 2 transistors, so you've got more impedance. So that gives you reduced drive strength, gives you reduced fan out, increased propagation delay. So how do you deal with that is the question. So when you've got transistors in VLSI, we sometimes need to start thinking about what the silicon looks like. So we'll just do that for a second. So if you put 2 transistors side by side, so they're in series, so you've got gate 1 and gate 2. So you've got your doped regions here. That gives us a stack depth of 2. We can imagine the gates being butted up to each other. Now, that's not quite 100% true, of course, because here you had a resistive path through the N, but that's usually an N plus, so it's a fairly low resistance. So it is fairly similar to this. So it's a bit like having 1 transistor with twice the gate length. And effectively, beta is halved. So what we do is we introduce stack depth into our gain equation. And so the gain now simply becomes exactly what it was before. W over L, we've introduced our stack depth S, which is 2 in this particular case. And then what we find, of course, is that that stack depth controls the threshold voltage and timings and so on. So we have beta N is halved. So if you make an AND gate from a unit width N FETs and 2.7 WNI, so it's matched P FETs to match the gain. Then, okay, so we can look at the threshold equation. We've seen this before. And what happens? Well, there's going to be a threshold shift basically because beta N is now half as big as it was before. So the threshold moves up in this direction here. So that's what you would expect to happen. So threshold shifts are undesirable. So just remember what happens. So you have some impedance M, and the timing is basically M times the capacitance and the ratio relative fan out FL over FD. So if you look up the PMOS, and that gives you your pull-up time, you get stack depth of P times the impedance MP. And so basically your impedances are increasing. And so gates with deep stacks are slower. I mean, this is to some extent inevitable, but there are things you can do, of course, by changing the widths. So how do you do that? So, okay, for NAND 2, we could just double the width of the NMOS transistors. That sounds like a fairly straightforward thing to do. For the NOR gate, you could just double the width of the PMOS transistors, because in the NOR gate, it's the PMOS that are in series. So you could just double the widths, and that just brings down everything to what it should be. But what if you've got a more complicated circuit? Okay, so you've got a more complicated circuit like this one here. You've got a P stack depth 3 in the green section, but in the red section, it was only 1, whereas you got an N stack depth of 2 everywhere in the blue. So that's not so immediately obvious what we do here, but again, it's relatively straightforward. You essentially work out the stack depth for each path, and you size the transistors on that particular path according to the stack depth. And that will match up the thresholds to that of a unit inverter, and will also match the drive strengths. So if it's uncompensated, you've got the stack depth coming into the equation, because we've seen that already. But of course, you can compensate it by changing your ratio of the width of the transistor, and basically the stack depths cancel out. So